Okay, welcome back to BME 2315. Today we're going to be continuing our discussion of regression, in this case the topic of general linear least squares regression. In the last lecture, what we did is we looked at how we could fit a single line, as you see here on the left, through a number of data points, and that came from a derivation of thinking about sum of squared errors, and we took the derivative of that surface with respect to each of the two parameters and found parameter values that would minimize the sum of squared errors. And that allowed us to, as I just mentioned, make predictions about new values of data points once we had fitted to others. Today we're going to talk about an expansion of that general approach called general linear least squares. And what that does is it casts us in a matrix form that's even more powerful. And what it does is it allows us to solve additional problems such as fitting surfaces or polynomials as long as they are linear with respect to the parameters. So it basically allows us to cast or expand our skill set to solve a wider range of problems. So to do that, I'm going to just kind of walk through this derivation rather than try to write out the whole thing, because I thought that this would be cleaner. Let me first draw your attention to the sum of squared errors that we saw in the last lecture, because that is like the same type of thing that we're working with now. And what you see, this is the current way that we're going to write it, that we've got a sum of squared errors, and we're going to be trying to find A's are going to be the parameters that minimize the fit between a model that makes predictions F, that's F, and data Y. And so let me just show you, over here on the right is where we have the model specified a bit more, where we see the data is going to be a vector of n elements, and so that's sort of n pieces of information we've gathered. And then on the right hand side, it shows that we're going to have m unknowns that are these m coefficients that we're solving for. And we can cast this in a linear algebra or a matrix form by saying that f equals z times a, where a are going to be our unknown parameters, z is going to be a structure based on the type of model that we're trying to predict, and f are the predictions from that model. Okay, so with that out of the way, let's look at how we can minimize the sum of squared errors. We start out by saying that we've got these squared errors right here, and if we multiply this out, we get ZA minus Y transpose times ZA minus Y, and then we use a rule that says that basically we're using FOIL on this polynomial to say ZA times ZA. So that's ZA transpose ZA minus the middle terms that are multiplied together plus the last terms that are multiplied together. And then we say that that's equal to the sum of squared errors. And this is set in a special, what's called a quadratic form of the sum of squared errors. And we're not going to go through all the derivations on this, but basically, if you have a set of matrices in what's called this quadratic form, then the gradient of that delta is given as 2ax plus b, okay? And so this is the 2ax and then plus b part of this. So we've got the gradient of the sum of squared errors is given to be right here. And then what we're going to want to do is set that gradient equal to 0, because we want to find a minimum. And so if we set all of this to the left-hand side equal to 0, then we have 2z transpose ZA equals 2z transpose Y, where this first part is known, the second part of A is unknown, and this last part is known. And so what we can now do is that using Gaussian elimination, we can solve for Z transpose Z given Z transpose Y. Okay, and so we can put that into NP linalg.solve, or you could solve it using a Gaussian elimination solver. Okay, we're not gonna solve or derive the quadratic equation and its gradient, but it's here for your reference if you'd like to see this further. Okay, so what we are going to do is focus on some more practical problems and look at how first we can solve the same problem that we did before, the line and fitting the equations for the line, and then we'll try to solve equations that we couldn't do before. So the first thing is noting the number of data points. So n equals 7 data points, and we've got n equals 2 parameters. Okay, and so we want to solve our equation like in a non-matrix form. We'd say that our equation is like this: a1 f is a2x, but in matrix form we're going to be saying that f equals za, where f is going to be 7 by 1, z is going to be 7 by 2, and a is going to be 2 by 1. That's why it was important to enumerate these values above here. Okay, and so then if we can write this out in matrix form, we're going to write out this f in matrix form. We've got f is f1, f2, dot dot to fn, which in this case is 7. We got a Z matrix. That's going to go down to xn. In this particular case, it would be x to the 7. Okay, and then we have an A matrix. A1 and A2. And so basically, all we need to do once we set up this matrix like here and establish the Z matrix like this is solve so that A equals solve ZTZ ZTY. Okay, and then we can make new predictions with f equals ZA. So basically what you're doing here is that you're taking the x values that you have and the y values that you have, then you're putting them in matrix form like this. You're solving for the unknown A matrix, and then you can plug in new x values into this same equation so you can make new predictions. I should say that I should say that the Python code for doing this for this particular problem will be provided at the end of the lecture. Okay, so that was nice about this. Let me flip back. Is that this gave a very compact way of expressing what we needed to do. That all we had to do is create the Z matrix according to the style that was asked for, and then there's a single line command to solve this system of matrices to get the answer. And so in a similar way, we can we can solve many other problems. So let me kind of show you the general approach, and then we'll solve particular problems. So first I'll write that f of I, this is going to be the general form of the types of models that we'll be dealing with. It can be given by f of I zi 2 plus dot 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 a m z I m. And these z's, so this is not just any x's. These z's are meant to be more general, so that the z's can be any function calculated only from independent variables. Okay, and so where n is the number of data points, m is the number of unknown params, and n is always going to need to be greater than or equal to m. Okay, so let me kind of write out the equation then that we have here. We have an F matrix and we get a Z matrix, Z11, Z21, Z12, ZNM, so you notice that these don't have to have the same dimensions, and they often don't. We often have more data points than we have unknown parameters. And these are our M unknown parameters. So we've got an F matrix, a Z matrix, and an A matrix. So the overall form of these equations is some F Z A. And as long as we can cast it in this form, the disease can be a variety of different things that can let us solve their models. And then if we can do that, if we can satisfy those criteria, then A can be given by solve Z transpose Z, Z transpose Y. Okay, so basically there's some work in setting it up, but solving it is very simple and allows us to have this a uniform solution. And then once you've got the A's, then you can make new predictions by repeating this equation, basically. But what you do is you calculate new z's, which are like the new places where you want the prediction, and then you multiply that with A to get f's. Okay, so we've already solved one problem using that. Let's solve something a little bit different. So let's solve something a little bit harder looking, which is a surface. And so the basic idea here is we've got two independent variables. xi, x1, and x2. Okay, and so the equation for this is fi equals a1 plus a2 xi1 plus a3 xi2. Okay, so we've got independent variable 1 and independent variable 2. So we've got n equals 6 data points. Okay, and we've got m equals 3 unknown parameters. Sorry, the pen is going slow on me again. Okay, 3 unknown params. And so then we can set up our z. So basically, that means that f to 6 by 1 equals z with 6 by 3 times a, which is 3 by 1. And you can see right there that the dimensions all work. Okay, so all we really need to do is set up our z matrix. So we'll do that here. We got z as being 1, 1, 1, 1, 1, 1. Okay, and then next is where we put these variables. So 0, 2, 2.5, 1, 4, 7, and then the next one, which is 0, 1, 2, 3, 6, 2. Okay, so that was x1 and x2, and then we simply now can solve this by saying a equals solve ztz zty. Okay, and then you make new predictions with f equals za. And so I know that it's difficult to see exactly what these values are right now, and so that's why I provide the Python code at the end so that you can test it and see exactly what these numbers turn out to be. Okay, so the last example problem we'll do is fitting polynomials, and it's just kind of yet another demonstration of how flexible this method is and how it can solve many different problems. So the general form here is we've got 7 data points, so n equals 7. Okay, and we've got and we're trying to fit a polynomial, and in this case we're going to fit a fourth order polynomial. So we're going to fit a cubic. Okay, so a cubic has 4 parameters to it. Okay, and so then z is going to be given by I'm not going to write out all of z. I'm just going to write out the first few terms here. So z is going to be written out by z x1, z x2, x1 squared, x1 cubed, and in general, all the way out to x1 to m minus 1. Okay, and so while that I'm showing it in a general sense right here, in this, if you're just fitting the cubic, then you just be using these 4 columns right here. So this is x2, x2 squared, x2 cubed, and so on. And the bottom number here is x to the n minus 1. So in this case, we would have 7 rows. So that's why, and then we'd have 4 columns if we're just doing the cubic, but we could do a higher order polynomial, which is why I'm drawing that here. But let me fill in these lower values because they could be useful to you. Okay. So it's written in a general way, but so that you can see what would happen if you were only doing a cubic. Okay, and then the solution to this is simply a let me just write a little bit more notation down here. So zi1 was 1, zi2 was xi, zi3 was xi squared, zi4 is xi cubed. Okay, and then to solve for this, we could say that the A matrix equals solve z t z z t y. Okay, and then to make new predictions, again we would use f equals za. Okay, so we've just solved or more we really set up 3 different example problems for you. And the reason why we just set them up is because the real computing happens then in Python. And so here I'll just walk you through the code for these 3 problems so that you can compute them and see what the answers are yourselves. So first off, for fitting a line, we're going to create a xt, which is the x values on a range from 1 to 8. Then we're going to make a z matrix that concatenates this. And this is what really follows the form of what we showed on the slides. And then you need to calculate the y matrix, which are the data points that we're going to compare this to. And then this down here at the bottom is the linear algebra solve command. This is the ZTZ. Let me write that down. Z transpose Z, and it's using the matrix multiply, and then is being solved against ZTY. Okay. In the next example, this is a little bit different in that we had 2 independent variables, so that's why we set up an x1 and an x2. And so when we stack them together to create the Z matrix, we have one column of 1s, one column of x1s, and one column of x2s. And then again we have the y values right here, and it's really the same solution right here. Okay, and then finally, when we're fitting a cubic polynomial, we've got a column of 1s, and then xt are the that shows the independent variables where we wanted values. So in this case, we wanted them from 1 to 8, and then this is the x is those numbers squared, and this is those numbers cubed. And then we're going to compare them to these numbers, which are our given data points, and then we can solve this system of linear equations again by doing the linear solve ZTZ and compared with ZTY. So I encourage you to try out that code yourself, and I'll be posting that as a separate file on our folder. So the key points from today's lecture is that linearly squares can be reformulated as matrices, and that allows us to recast a much larger general set of complex models involving multiple independent variables or nonlinearities in the equations, as long as the equations are linear with respect to the parameters. So I hope that was helpful to you, and I'll see you next time.